Hi students, this is the section, the addition rule and rule of complements from chapter probability. The objectives for this unit is to be able to compute probabilities by using the general addition rule, by using the addition rule for mutually exclusive events, and to be able to compute probabilities using the rule of the complements. I would like to start with the definition of a compound event, which is an event that is formed by combining two or more events. Could be 2, 3, 4 different events combined together. For example, let's take the event of today is Tuesday, and the event of today is raining. We can have today being Tuesday but not raining. We can have today being raining but not being Tuesday, and we can have a day that it's both Tuesday and it's raining, or we can have a day that it's neither. It's not Tuesday and it's not raining. But the union of the both events together, today being Tuesday and raining, it's a compound event. To calculate the probability of event A or event B happening means to compute the probability of only event A happening, probability of only event B happening, or the probability of both A and B happening at the same time. It's important to understand the difference between or and when it comes to probability. The probability of event A and event B happening means both. And we're going to be using this intersection notation, which is like an upside U, to denote the probability of both A and B happening. We're going to be using the symbol of union, which is looks like a capital U. It's not a U. It's a symbol for denoting the probability of, for denoting the event A or B happening, and for the probability when finding the probability of A or B. In this case, or means either or both happening at the same time. Let's take this simple example to be able to distinguish between and or. I hope you have played Uno before. When playing Uno and somebody puts a card, somebody puts this card, we can either put a 4, any color, or a yellow card. So this would be 4 or yellow, any of the yellow cards or any of the 4 cards, no matter what color. I hope you can understand the difference. This is 4 or yellow, and this is 4 and yellow. Let's take a look at some simple examples. There are 25 students in Mrs. Bush's 6th grade class, and on a cold winter day in February, many of the students had runny noses and sore throats. After checking each student, the nurse constructed the following table. We have 6 students having a runny nose and a sore throat, 12 students having a runny nose but no sore throat, 4 students having no runny nose and a sore throat, and 3 students having neither, not a runny nose, not a sore throat. Notice that we have a total of 25 students if we add them all up. If we wanted to find the probability of selecting a random student having a runny nose, let's practice a little bit with our notation. This will be the probability of runny nose. I have to take the number of students that have a runny nose and divide it by the total number of students. What I want divided by what I can get. If you don't remember this formula or you don't know this formula, please go back to our previous video, Basic Concepts of Probability, from the same chapter, Probability. What I want is any of the students having a runny nose, sore throat, or no sore throat. That's a total of 18 students. What I can get is any of the 25 students when randomly selecting a student. 18 out of 25 is 0.72, or in percentage form, 72%. when selecting a random student, we have 72% chance that it will have a runny nose, either with a sore throat or without a sore throat. If we want to find the probability of a randomly selected student having a sore throat, now we're going to take a look at the students that have a sore throat, runny nose and no runny nose, because we're not being specified. What I want divided by what I can get. What I want is any of these 10 students. What I can get is any of the 25. 10 out of 25 is 0.4, which is 40%. We have 40% chance of selecting a student that has a sore throat out of the 25 students. If we want to find the probability of selecting a random student having a runny nose or a sore throat, that could be any of the students that have a sore throat or any of the students that have a runny nose. We have a total of 22 students, which would be what we want, out of 25 in total. If we divide 22 by 25, we get 0.88%. Sorry, 0.88, which is 88%. If we want to find the probability when selecting a random student of getting a student that has neither a runny nose nor a sore throat, that means one of the students that have none, no sore throat, and no runny nose. We only have 3 students that do not have a sore throat and do not have a runny nose. 3 out of 25 is 0.12. What I want divided by what I can get. 12% of the students do not have a sore throat and do not have a runny nose. If we want to find the probability that a student has a runny nose but does not have a sore throat, out of the students that have a runny nose, we're going to only select the ones that do not have a sore throat, which is a total of 12 students. What I want divided by what I can get, 12 out of 25, it's close to 50%, 48%. All right, now I want you to pause this video after I showed you the data, and I want you to attempt and construct your frequency distribution with the information provided. A recent study of 300 patients found that of 100 alcoholic patients, 87 had elevated cholesterol levels, and of 200 non-alcoholic patients, 43 had elevated cholesterol levels. If a patient is selected at random, we want to find the probability that a patient who is an alcoholic has an elevated cholesterol level, who's a non-alcoholic, and a non-alcoholic patient with non-elevated cholesterol levels. I want you to construct a frequency distribution before we find the probabilities. If you need a hint, this will be the table that I want you to complete. I want you to organize the data for those 300 patients in this table. We're being told that 87 from the alcoholic patients had elevated cholesterol levels, and 43 from the non-alcoholic patients had elevated cholesterol levels. That puts our data like this, 87 and 43. Also, we're being told the total of alcoholic, which is 100, and we're being told the total of non-alcoholic, which is 200. Just by subtracting, we can find that we have 13 alcoholic patients that didn't have elevated cholesterol levels, and 157 non-alcoholic that did not have elevated cholesterol levels. Let's just keep in mind that we have 300 in total. Let's find our probabilities. The probability that an alcoholic patient, that we get when selecting at random, an alcoholic patient with elevated cholesterol levels is 87 out of 300, which is our total number of patients. What I want divided by what I can get. It looks like we have 0.29 or 29% probability of getting a patient that is an alcoholic with an elevated cholesterol level. A non-alcoholic patients are all of these with or without elevated cholesterol levels. Remember, this was 200 out of 300, that's 2/3, which is 0.66 or 0.6666. In percentage form, it will be 66.67% if we round to our nearest decimal, 100 place. The probability of finding a non-alcoholic patient with non-elevated cholesterol level will be 157 out of those 300, which again, it looks like it's going to be close to 50 because half of 300 is 150. What I want divided by what I can get, 52.33% is what I got. And it keeps on going to 33. It's important that you read your question and comprehend what you're being asked so you can select the right portion of the table to answer your questions. Now, let's learn the general addition rule. When computing the probability of event A or event B happening, or the union of event A and B, we add the probability of event A plus the probability of event B, but subtract the intersection. This is because whenever we're talking about the probability of A plus the probability of B, we're counting whatever is in both twice. This will be better understood if I show you with a Venn diagram. Let's suppose the whole square is all of our sample space, all of the possibilities. Event A is the circle A, event B is the circle B. The probability of event A is just all of the possible outcomes that are inside of this circle. The probability of event B are all of the possible outcomes that are clustered inside circle B. When you add these two, the probability of A plus the probability of B, if you notice, we're counting this intersection twice. That's why we subtract one of them. That minus the probability of the intersection A and B. We don't want to count it twice. This doesn't happen when you have a table. If you noticed before, we just select our values. But in the case you have those probabilities, those percentages of probabilities, we use the general addition rule. Probability of A plus probability of B minus the probability of the intersection. Now, remember that there's a difference between or and and. If we're talking about the probability of A or B, remember the symbol union, we're talking about the probability of event A happening, let's suppose only A, the probability of event B happening, only B, and the probability of both happening at the same time. This is the probability of A or B, or the probability of A union B. If we're talking about the probability of their intersection, A and B, both happening at the same time, which is and, we're only located in this intersection here. There's a difference between the two, and it's important that you understand that you learn how to differentiate or and. Let's take a look at our example 3. The chart below shows the numbers of endangered and threatened species both here in the United States and abroad. We have different categories: mammals, birds, reptiles, amphibians. If we choose one species at random, any of them, the species, any animal, what's the probability that we get a threatened species in the United States from the threatened species only? Notice how we're being told from which species we're choosing from. This will be what we can get in our formula, what I want divided by what I can get. What I want is any of the species inside the United States that are threatened, which is all of these right here. I got 170 for this total. Out of any of the threatened species, we have if I add all of these, 68 plus 251 plus 77 and so on all the way plus 8, I get 668 threatened species. What I want, what I can get, 170 out of the 668 gives me 25.45%. I'm gonna round to the nearest tenth because I don't have enough space. In your assignments, you follow directions on what they ask you to round to. If we choose one species at random, what's the probability that species is threatened in the United States, but this time from both endangered and threatened species, from all of them, from the endangered and the threatened? From our previous example, we had that this column was 170, which is the species in the United States and threatened. Out of all of them, we have to add 668 plus the total of 98 endangered species, which is 170 divided by 766. That gives me 22.19%. If we choose one species at random, what's the probability that it is endangered, an endangered foreign bird from all of them? Remember, all of them in total, we had 766. What we want this time is endangered foreign bird. Endangered foreign bird, which is right here, only 6. What I want divided by what I can get. 6 out of 766 gives me 0.0078, which in percentage form is 0.78%. If we choose one species at random, what's the probability that this species is an endangered foreign bird, but only from the threatened species? This time, what we can get is any of the threatened species. These are our threatened species, which were 668, right? An endangered foreign bird is right here. Endangered foreign bird. Only 6 endangered foreign birds. But notice how that 6 is not part of what I can get. I cannot get an endangered foreign bird that is threatened. Those do not happen at the same time, which means our probability for this is 0%. If we choose one species at random, what's the probability that this species is a mammal or a threatened foreign species from the threatened species only? Again, we're only choosing from the threatened species, which is this portion right here, which previously we have learned that it was 668 in total when we add them all up. A mammal or threatened foreign would be any of these two mammals, 68 plus all of the foreign, which are 251 plus 175 plus 64 plus 8. When I add all of these up, 68 plus 251 plus 175 plus 64 plus 8, I get 566. That's what I want. What I can get is any of the 668 species. If I divide what I want divided by what I can get, I get 84.73%. If we want to find a mammal or threatened foreign species, but this time from all of them, the threatened and the endangered, this is what I can get, any of them. which from previous slides, we learned that it was a total of 766. But what we want is any of the mammals or the foreign species. Notice the keyword or, either or. We had gotten that it was 566. What I want divided by what I can get, I have a total of 566 that I can get out of all of the threatened and endangered species, which is 766. That would be 0.7389, which is 73%, 0.89. Now let's talk about mutually exclusive events. Two events are said to be mutually exclusive if it is impossible for both events to occur at the same time. For example, if we go back to that example where we're looking for the probability of an endangered foreign bird out of the threatened species, that was not possible. Both events cannot happen at the same time. Those are mutually exclusive events. And just like in this example, mutually exclusive events happening at the same time have a probability of 0. Here's some examples of mutually exclusive events. A number being even and odd at the same time, drawing a card from a deck of cards that it's a club and a heart at the same time, or a day being Monday and Saturday and Friday at the same time. I want to remind you from our Venn diagrams that we had the probability of A being the collection of events of event A happening. The collection of event B happening is the probability of B. The probability of their union is both A, B, or both A and B together. The probability of their intersection is just when A and B happen at the same time. Thinking about these Venn diagrams, I want you to picture mutually exclusive events. When you have mutually exclusive events, those circles do not overlap. You don't have an intersection for them, which is why our probability for mutually exclusive events happening at the same time is 0, because we cannot have them happening at the same time. For example, getting an ace and getting a kings. It's either or. You cannot have an ace king when you draw a card from a deck of cards. But if we were talking about the events getting a heart or getting a kings, we do have one card that it's both a king and heart. Hearts and kings would be not mutually exclusive events. Aces and kings would be mutually exclusive events. Now, a clinic offers, for example, a clinic offers 2 tests, A and B, for detecting a disease. We have a probability of 0.6 or 60 for test A being positive. We have a probability of 0.50 or 50% for test B being positive, and the probability for their intersection, meaning both A and B being positive at the same time, of 30% or 0.3. We want to find the probability that a patient tests positive on either test A or B. Either test A or test B. Using that formula that we learned in the previous slides, I don't know if you remember, the general addition rule, we can answer this question. We do not have a table that we can take a look at the data and just add our values. This time we're given the probabilities. We have to add the probability of A plus the probability of B and subtract that intersection, because remember, we counted that intersection twice. The probability of A is 0.6. The probability of B is 0.5. And I have to subtract that intersection, which is 0.3. Looks like my probability of A or B, for probability for test A or test B being positive, is 0.8, which is 80%. We use the formula. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B happening at the same time. In this case, tests A and B being positive. What's the probability that a patient tests positive on test A but not test B? We do know the probability of testing positive in test A. It's 0.6. This is 0.6 or 60%. The whole thing. But I want only test A, not test B, which means I'm looking for this portion right here only. What would I need to do? I need to subtract from the probability of A, the probability of the intersection. I'm going to take away this intersection. What's the probability for the intersection? 0.3. The probability of A minus the probability of the intersection of A and B. That is 0.6 minus 0.3, 30%. Similarly, if I want to find the probability that a patient tests positive only on test B, but not test A, we're looking for this section right here, and we have to repeat the same steps. I'm going to take the probability of B, which is 0.5, and subtract the intersection, because I want to take the intersection away, 0.3. 0.5 minus 0.3 is 0.2, which means there's 20% chance of testing positive only on test B. If you want to, you can start already labeling all of your probabilities in each of the individual sections, which could help you find your answers faster for the following questions. What's the probability that a patient tests negative on both tests? We do know that the probability of only A is 0.30. We know the probability of both of them is 0.30. We know the probability of only B is 0.2. We want the probability of testing negative on both tests. That means neither A or B, outside over here. If we know that the collection of probabilities adds up to 1, how can I find the outside portion? Being outside of A and outside of B, which means testing negative on A and testing negative on B. 1 minus 0.30 minus 0.30 minus 0.2 will give me 0.2, because the collection of A or B, as found in the previous question, I think it was like the first one, we got that the union of them was 0.80. The remainder would be 0.2, or 20% chance. Again, if you want to, you can label all of your probabilities in each of the individual sections. Outside of both would be 0.2. Only A would be 0.3, only B will be 0.2, and their intersection testing both positive for both A and B is 0.3. What's the probability that a patient tests positive on exactly one test? Oh, that means either only A or only B. That's 0.2 plus 0.3, 0.50, or 50% chance. What's the probability that a patient tests negative on test A but positive on test B? Negative on test A, so outside of test A, everything on the outside, but positive on test B, so only test B. We had already computed that. That was 0.2, 0.2. Again, it's very important that you read your question and comprehend what your question is asking you to find. What's the probability that a patient tests negative on test B but positive on test A? Positive on test A and negative on test B is only A, which we had previously computed. It was 0.3 or 30%. What's the probability that a patient tests negative on test A or test B? Let's find out. Testing negative on test A or test B. Remember, that means either negative on test A or negative on test B or negative on both test A and test B. Negative on test B is all of these outside of B. Negative on test A is all of these outside of A. Looks weird, but let me choose a different color. Negative on test A would be outside of A. Sorry. Outside of A, everything on the outside. Since it's either negative on A or negative or on B, or both, negative A and B, it would be both combined, which means the only piece that it's left out, it's this one right here. If we know the union is 0.3 and the whole thing is 1 or 100%, we can just subtract 1 minus 0.30 or 100% minus 30% to find our answer. Or you can add the values. Remember, we had 0.2 on the outside, 0.3 for only A, 0.3 for both A and B together, and 0.2 for only B. Again, 0.2 plus 0.3 plus 0.2, that's 70. 0.70 or 70% chance that a patient tests negative on test A or tests negative on test B. What would be the probability that a patient tests positive on both tests or negative on both tests? This time we're looking for positive on both tests or negative on both tests, which is outside of both. Because on our previous questions, we had already found the probability of neither, which was 0.2, and from our value or information given, we know that the probability of both happening at the same time is 0.3. All we have to do is just add them. 0.3 plus 0.2, that's 0.5 or 50%. What's the probability that a patient tests positive on at least one test? So either A or positive on only B or positive on both A and B. Looks like the union. The probability of A plus the probability of B minus the probability of both. We had already found that it was 0.8 or 80%. So like a marathon of questions. I want to introduce you to another definition or another formula. When you have mutually exclusive events, remember those events that cannot happen at the same time, the probability of their intersection is 0 because those circles do not touch each other, do not intersect. All you have to do when computing the probability of mutually exclusive events, when you're finding the probability of either or both, is just add the probability for each, whether you have 2 mutually exclusive events or multiple mutually exclusive events. And our last definition for this video, the complement of event A. If we have any event being, we're going to label it A, the complement of event A, it means when event A does not occur. And we're going to use this notation, A with a little c superscript, which means the complement of A. If A is whatever is compilation of events, it's clustered in this circle, not A or the complement of A would be everything outside of the circle. This yellow portion right here will be the complement of A, everything on the outside of A. If you have multiple events, it's still everything outside of A. If you have only the event A, well, the remainder, whatever not A is going, the probability of not A happening, it's the complement. For example, if we have the event of A being today is Tuesday, the complement would be every other possibility. Monday, Wednesday, Thursday, and any of the weekend days, Friday, Saturday, and Sunday. The complement of today is Tuesday is today is Monday, or today is Wednesday, or today is Thursday, or today is Friday, or today is Saturday, or today is Sunday. Here are some important rules about the complements. Those are mutually exclusive. A and the complement of A cannot happen at the same time. Either or can happen, but not both of them together at the same time. If we add the probability of A plus the probability of its complement, what do we get? A whole. We get all of the sample space, all of the possible outcomes. The probability of A plus the probability of the complement of A is always going to be 1, which is where we got this rule of the complements. The probability of the complement of A is 1 minus the probability of event A. If I take all of my probabilities, the complement of A and A, I get 1. Well, 1 minus the probability of A is the probability of the complement. And that's our last definition for this video.